and welcome. I am Karen Fox with NASA's Office of Communications, and we are here today at NASA Kennedy in Florida to talk about our newest astrophysics mission. This is the Imaging X-Ray Polarimetry Explorer, which is launching in the wee hours of Thursday, December 9th at 1 a.m. East Coast time. We are following CDC and NASA COVID guidelines today. Everybody in the room is vaccinated. We will be wearing our masks. However, individuals will take them off to speak. We will be taking questions after our speakers go. We'll be taking questions from those in the room. We'll be taking questions from those on the phone. And we're also welcoming questions from social media. So send them in with hashtag #AskNASA, and we will try and answer some of those as well. Our lineup today, we have Brian Ramsey, who is the Deputy Principal Investigator for IXPE at NASA Marshall in Alabama. We have Elisabetta Cavazzuti, who is the IXPE Program Manager for the Italian Space Agency. We have Luca Baldini, the Co-Principal Investigator at the Italian National Institute for Nuclear Physics. And at the far end, MacKenzie Ferrie, who is the IXPE Program Manager for Ball Aerospace. And with that, I'll pass it to Brian to kick us off.
Thank you. So IXPE is going to open a new window on the X-ray sky, that of imaging polarimetry. So that's going to give us two completely new measurements that are going to help us understand how some of the most dramatic and energetic events in the universe take place. X-ray. So the sort of objects that we're going to be looking at extremely energetic events. We're going to be looking at black holes, neutron stars, matter funneling down into very compact objects, just matter is sort of the extreme end of the scale. These measurements that we'll make, we'll be looking at material funneling down onto black holes and getting heated to incredibly high temperatures, millions or tens of millions of degrees. And we'll also be looking at matter that's accelerated in incredibly high magnetic fields. And both of those mechanisms produce polarization. And so polarimetry will be a very powerful tool for probing the emission mechanisms of these very exotic sources. So I'm going to go back to how IXPE started, and it really begins with our principal investigator, Martin Weisskopf, who in the early 70s, if I could have the first picture, please. Right. So there's Martin at the front there, in front of the rocket. So in the early 70s, he made the first measurement of polarization from the Crab Nebula. And that was followed up a few years later in the late 70s by a small instrument that was on OSO-8. That was a satellite mission, and that confirmed the measurement. And the interesting thing is that that remains one of the few measurements of X-ray polarimetry, despite 50 years having passed. And the reason for this is that polarimetry is a very difficult thing to do. You need a dedicated mission that can look for really long periods of time at the stars that sources we're interested in. And then you also need an extremely sensitive instrument. And so that brings us to IXPE. So IXPE is a NASA Small Explorer. It's a collaboration between NASA and the Italian Space Agency, with also a contribution from Japan as well. So if MacKenzie could point, I will just quickly give you an overview. So IXPE contains three identical telescopes. So at the top, we have a mirror module, and then down below, there is a polarization-sensitive detector. So there are three identical telescopes, and they sit on top of a Ball-provided spacecraft at the bottom there. Then the observatory also features an extendable boom. So it is stowed for launch, and then when we get into orbit, the boom will extend, and it will put the mirror modules at the correct focal distance. So just going on and talking about the instrument a little bit, the mirror modules were fabricated at Marshall Space Flight Center. They're technically quite challenging. Each mirror module contains 24 concentrically nested mirror shells. They're made of metal, and they're very thin, thickness of a few sheets of paper. And the reflecting surface is incredibly smooth. So to efficiently reflect X-rays, you need a surface that's about smoothness of about 1,000th the wavelength of light. So we have that on every one of these mirror shells. And so these mirrors focus the X-rays. They collect X-rays from about a 12-inch diameter area, and they focus it down to a tiny spot on the detector, which is about a half a millimeter, about 20,000ths of an inch in diameter. And when you do this, you drive the background down by a considerable amount. The background is proportional to the size of the detector. So if you can focus all of your X-rays to a tiny spot, you drive the background to almost nothing, and that gives you a very large increase in sensitivity. Completing these mirror modules, we have, and this is the Japanese contribution, very thin membranes on the entrance and the exit of the mirror modules. And these membranes are there to control the temperature. So they're coated with aluminum. They're extremely thin, about a 20th the thickness of a human hair. So they let through the X-rays very efficiently, but they stop heat from radiating from inside the mirror module, and that allows us to keep the mirrors at a nice, comfortable room temperature. So those mirrors focus the X-rays down to these remarkable detectors that are provided by our Italian colleagues, and that's what provides our polarization sensitivity, and Luca will tell us about those in a short while. So that's the payload. IXPE nicely complements other missions that are currently flying. We have missions that specialize in, say, angular resolution or spectroscopy or different wavelengths, band or timing. And so IXPE offers something unique and adds to that mix so that we get a much broader picture of the X-ray sky. As I said at the beginning, we're going to be looking at very dramatic objects. So we're looking at black holes, exploding stars. We're looking at very intense magnetic fields, 1,000 million times the magnetic field of the Earth. So we're very excited about this mission. We're very anxious to get on orbit and start probing the mysteries of these very exotic sources. So, hand back to you.
Thank you so much, Brian. We are going to now go to Elisabetta Cavazzuti, who is going to talk to us a little more about what happens after launch.
Yes. So let me say at the beginning that the launch on November 9th is not the end of the story. It's just the beginning. It's a very, very key point in the mission where the payload, the telescope, and the spacecraft will experience a very hard time for which we have built it very robust. And it will be inserted in a low Earth orbit at 600 kilometers around 0.2 degrees of inclination, so an equatorial orbit. And you must remember that the success of a mission is driven by its scientific results. So now we face the next 2 years, the duration of the operation phase, the operative phase of the mission, in which scientists all over the world will work together. And if I can have my first slide, you can see how IXPE is made of international collaboration, which spans all across the world. And it's made by people, instruments, and facilities. And the observatory will talk to the Earth in 6 or 7 times a day to the primary ground station provided by Italian space agencies and located in Malindi in Kenya, which is equatorial, and with a backup ground station which is in Singapore. Then the joint venture, the partnership between Ball Aerospace and Colorado University LASP will run the Mission Operations Center, which is located in Colorado. And it runs the spacecraft. It means that sends telecommand and receives telemetry from the observatory. And it talks to the Science Operations Center, which is in Alabama, run by Marshall Space Flight Center. The Science Operations Center duty is to send to the Mission Operations Center the observatory plan every day, which source to observe for how long, and it works with the Italian Space Science Data Center in Roma, which has contributed with the international team to the scientific pipeline, which elaborate, analyze, and distribute the data. So when the data will be back and analyzed by scientists, they will be ready to be distributed by NASA Center HIASARC in Greenbelt, and it will be distributed within 1 week after the end of each observation, except for the first 3 months where we need to be sure that data are well analyzed, because, as Brian said, it's the first time ever we fly a polarimeter with imaging capability. So we like to distribute data which are confirmed and robust. So at the end, we have this international collaboration, which is also coordinated by a science advisory team co-chaired by Stanford University and Roma Tre University. So, and then we have Japanese who contributed to the detector. So you can understand how wide is this collaboration. Then I will conclude my speech with the contribution from the Italian Space Agency, which led the Italian contribution. The heart of the instrument is this polarimeter, which MacKenzie showed you. It is at the focus of each mirror module, and it hosts a gas pixel detector, which Luca will describe you in detail. And it has been designed and tested by the National Institute for Nuclear Physics in Italy and calibrated by the National Institute for Astrophysics. The detectors includes also a detector. The instrument includes also a detector service unit, which is a commands the focal plane and the instrument. Inside the detector, we have also a filter and calibration wheel, which is on top of the detector. It carries filters which will allow the team to calibrate the detector while in orbit. This is very important to keep the detector well trained, let's say. Okay. And finally, we have, in these two contributions, the detector service unit and filter and calibration wheel, are part of the Italian industry contribution by OHB Italia. And so I can't wait to see our first result, and I go back to Karen. Thanks.
Thank you so much, Elisabetta. Next up, we have Luca, who is going to tell us a little bit more about the detectors themselves and what kinds of science we can expect from IXPE.
Thank you, Karen. I'd like to go back to the detectors for a second. And so photons come with this exotic property that's called polarization. And really, polarization has to do with the direction of the plane where the electric field of the X-ray oscillates. When an X-ray interacts with our detector, what happens is that the photon disappears and an electron appears in place. And what we're trying to do is to follow the footsteps of this electron and reconstruct the direction of emission, because that's key. That's our basic proxy to recover on a statistical basis the polarization direction of the incoming radiation. So the detection principle is very simple, and I think this is also what makes these detectors beautiful. And now, if I can have my first animation, I'd like to walk you through the path that an X-ray takes from the source to IXPE. The first element that it encounters, it's the mirror module assembly that, as Brian said, has the function of focusing X-rays on the focal plane. And 4 meters down the road, here's the interaction with the detector and the track that's created and collected on a readout plane. Now, you might wonder if it's really that simple, how it took you guys so long to come up with this. And the answer to that is that, well, the tracks of these electrons are really small. They're less than 1 millimeter long, and it really takes a fairly high granularity to resolve those tracks. And so this is an identical copy of the detectors that is going to fly on IXPE. And so this, as Elisabetta said, is the heart of the focal plane, and particularly this tiny readout chip. So that's really what makes you know, the IXPE mission possible. And so in a sense, you might say that all that IXPE is about is for, you know, waiting for X-rays emitted by these sources far away to travel through the universe and get to this tiny detector, to this tiny readout chip that's sitting in the focal plane. Now, if I can have my second picture, I'd like to switch gears here and talk about one of our most important sources. This is called Cassiopeia A. It's a supernova remnant, and it's a very complex system. It's very rich in physics. So if you imagine a supernova remnant, it's what remains from a stellar explosion. And if you imagine taking a star like the sun and squeezing it to a sphere that's like 20 kilometers across, that's something that resembles a neutron star that sits at the center of the remnant. And then on top of that, you have the blast wave from the explosion, which is where the galactic cosmic rays are believed to be accelerated. This is a very important source to us. It's going to be the first source that we will observe in our program. And one of the peculiarities, as you see, is that it's extended, and you know, being the capital I at the beginning of IXPE imaging, you know, that's the source extension. It's you know, one of the key points here. So with IXPE, we're not going to get one single image of this source. We're really going to get 3 different images at the same time. One is the intensity map, which is, you know, the same thing that most of the other imaging instruments do, like Chandra. But in addition to that, we're going to get 2 more images, as Brian said, of the polarization degree and the polarization angle. And this is really the new information that IXPE will bring to the table, and all the other conventional X-ray detectors are just blind to. So I think I can say we all can't wait to find out, well, what IXPE will see. And with that, I'm going to pass it over to Karen.
Thank you so much. We will finish up with MacKenzie Ferrie from Ball Aerospace, who's going to explain a little bit more about how this spacecraft came together.
Yeah, so you guys all got to hear about the great science that IXPE is going to produce. And Ball Aerospace is extremely excited to be part of this collaboration. We actually were partnered to fabricate, assemble, and integrate and test the observatory. As you heard from Brian and Luca, the mirror module assemblies up here were contributed and built at Marshall Space Flight Center, and then the instruments down here were contributed by the Italian Space Agency. We received these and integrated them into the observatory, along with the spacecraft bus. So the spacecraft bus is an integral part of the observatory because it is what commands and powers everything on the observatory. Currently, the observatory is in its launch configuration. Obviously, we're getting ready for launch in a couple days. And in its launch configuration, it's actually much more compact. It's about the size of a refrigerator, if you can believe it. And eventually, in order to meet the X-ray requirements that Brian and Luca have both mentioned, we need to be 4 meters away, the MMAs, to the instruments. And in order to do that, we have this deployable boom here in the middle that Brian pointed out. It's an origami kind of like structure, and in space it will deploy kind of like a jack-in-the-box. And then get the MMAs and the instruments in their proper location in order to get that science data. Also, as I mentioned, Ball Aerospace is responsible for testing the observatory at the factory. And testing is so important for the observatory. It really is the testament to say that it's going to survive all the different environments it's going to see. One in particular is launch in a couple days. It's a really rough ride to get up there. It's not smooth. So we need to shake it and induce loads into the observatory to ensure that it's going to make it up into space. Also, in space, it's going to see a lot of different temperature changes. So we simulate those temperature changes in the thermal vac testing. That you will see in my first image here is actually of the observatory deployed in our Titan thermal vac chamber. So this is where we simulated all of the different temperatures that it'll see in space. After launch, as Elisabetta had mentioned, this is kind of where the fun starts. We get to operate it. So Ball Aerospace is also part of the commissioning and the mission operations of the observatory. We are partnered with the University of Colorado, LASP. And what's fun about this partnership is that not only do we get to work with the university staff, but we get to work with the students as well. So the students are going to be the folks operating the observatory up in space for the next coming years, along with Ball, our Italian partners, and Marshall as well. In my next graphic here, if we could pull that up, we can show you what is going to happen in space. So when we first get up there, the first thing that's going to happen is that the solar arrays are going to deploy. And this is very important because this is what will charge our battery to the full capacity so that we can then start turning all the other elements on. Commissioning is about 30 days long, and on about day 7 is where you will see the boom deploy here. And that's where we will get the mirror module assemblies and the instruments in their proper location so that we can start taking the wonderful science data that you get to see eventually. So I'm really excited. I know everyone else has said they're very excited. So with that, I'll hand it back over to Karen for questions.
Thank you so much. We will start the process of taking questions now. We will work from the room first. We will also take questions on the phone if we have them. And then, of course, we still are taking in our social media questions with hashtag AskNASA. So please do submit those as well. Any questions from the room? Amy Thompson.
Hi, thank you. Amy Thompson from space.com. So I was just kind of wondering how IXPE differs from, say, like the Chandra Observatory, and what kind of science that you're going to be able to do with this that you haven't really been able to do before. Like I know in some of the releases it was talking about spin rates of black holes. So I was wondering just like how important is it to know that, and what does that tell you about a black hole?
What do you think, Brian? I think that's yours.
Lucas, yeah.
And you can take your mask off if you'd like.
Yeah, sure. Yeah, so you mentioned Chandra, and of course Chandra is a great observatory that's up flying right now. And Chandra sort of specializes in imaging. It has extremely high angular resolution, and also spectroscopy. It has gratings. And so that provides certain amount of information, on a source. But whereas IXPE is doing something completely new, it's measuring this polarization. And the polarization is a measure, for example, of the magnetic fields that are present in a source, how strong those magnetic fields are, and we think it's the magnetic fields in many sources that's producing the energetic particles that produce the X-rays. And so by making those measurements, we're getting a sort of a unique look at the at sources. And you mentioned the spin of a black hole. Yes, IXPE can do that. We expect that the polarization will be curved in the space around the black hole. And so if we look at different energies, we can look deeper and deeper into that accretion disk and get closer and closer to the black hole. And we can measure the spin of the black hole in that way. And that provides a fairly clean measure of the spin of the black hole.
Great.
Yeah, okay.
Thank you, Brian. We are next going to Jeff Faust with Space News, calling in on the phone, please. Go ahead, Jeff.
Two questions for whomever wants to take them. One, I'm just curious about the choice of the orbit, the 600-kilometer, 0-degree inclination orbit. What factors drove that particular orbit choice? And then what's the limiting factor in the lifetime of the spacecraft? Is it the degradation of the detectors, consumption of fuel? What would sort of limit the lifetime of the spacecraft beyond the 2-year primary mission? Thank you.
Okay. So I can try and take that. So first about the orbit. The altitude is fairly standard for the low Earth orbit environment. The inclination is very important to us because in equatorial orbit, the cosmic ray background, it's minimum. And so that's kind of the best orbit that you could possibly shoot for in terms of the background from charged particles. And I forgot what was the other question? Oh, the lifetime. So in principle, there are no consumables on the mission, and so there's not a hard limit on the duration of the mission. The gas pixel detectors are sealed, and we expect the performance of the detectors not to change measurably with time. So we're aiming for these 2 years prime phase of the mission, but if everything goes well, I think that it's very possible that we can aim for an extension.
If I could just add to that, we have a NASA requirement to deorbit within 25 years, and so this is really the highest orbit we can put it in and still meet that requirement. So right now we're predicting 18-year for re-entry.
Great, thank you. We will start taking some social media questions, though again, questions from the phone are still welcome or in the room. Just let me know if you have those. But first up, I think this question is for MacKenzie. It's a question from Twitter. What was the biggest challenge that Ball faced in integrating the components of IXPE to the bus?
So I think the biggest challenge we had was the alignment of the MMAs and the instruments. So actually, as this deploys, it actually spins around until it then gets to its final distance up here. And so there was a lot of testing that we had to do on the ground to ensure that two things, that we were achieving the focal length that was required of the 4 meters. And so we had to do a lot of alignment there, but also that after it finished its full deployment and was up here, that these were in the proper location so that when the X-rays come through the MMAs, they hit the collimator down here of the instrument. I think that was kind of the hardest thing so far.
Great, thank you. Another question, this one is from our virtual NASA social. How far away are the objects that IXPE is going to look at, and are any of them close by? Is that a Brian question, or?
I'm not sure. Do you know the closest?
So we're gonna observe an entire range of different objects. Some of them are in our galaxy, so they're gonna be a few kiloparsecs away. On top of my head, I wouldn't know which the closest object would be, but I'm sure that we can pull that information out. We're going to observe a handful of extragalactic objects as well. So those would be objects much, much more far away and more violent because, for them to have a flux that's detectable by IXPE, it means that they're really special. So
the whole range.
Yeah.
Great, let's go follow that up with another science question. This is from Chris on Twitter. Will IXPE be able to study the polarization of relativistic jets at the poles of supermassive objects? And I'll ask you to help us all understand what a relativistic jet at the pole of a supermassive object is as well in your answer.
Luca, would you like to take this?
Sure, I'll try. Some of the most violent objects, and we're talking about mainly objects that are extragalactic in origin. The magnetic field is such that the emission is very asymmetric, and so sometimes, they have accretion disks, they can have jets, and the way you see those objects depends on the orientations of the source with respect to the line of sight. So the answer to the question is yes. We're gonna at least try and study the polarization of some of those objects. SNA, it's an example where it's one of those systems. It's resolved by IXPE, so we can try and study the polarization of the core of the source and of the jet. I don't think it's taken for granted that the polarization is high enough that we will actually measure something, but at the very least we can put upper limits on the degree of polarization, which is also interesting in terms of understanding the physics of the source.
If I can add something on this, we're also going to observe the same type of source as SNA, but when its jet is oriented toward us, which are named blazars. And so a couple of these would be also in our lists. So it's where the relativistic and Doppler effect enhance the emission and possibly even help in detecting polarization. So same object, different orientation toward the observer.
I really think that's one of the most exciting things about this mission is just these really violent, exciting, dynamic things that are happening that we are studying. And we're definitely getting questions about black holes. I may go back to some of those. But for now, in terms of social media, two length questions. I'm combining two people's questions into one. How long did it take to build the spacecraft? And how long before we get our first observations?
So I'll take the first question. So we started the integration of the observatory back in December of 2020. We also started actually cutting chips earlier in 2019. So it's been a couple years. The entire observatory integration and test phase was really about 8-9 months. From start to finish. But it's been a couple years for the whole thing since we started cutting the first chips of the structure. As for the second question, I'll hand that off to Brian.
Sure, I can do that, yes. So as Luca mentioned, our first observation is going to be in our science program, I should say, because we pointed a few sources just to check the system out during the commissioning. But in the science phase, our first real target is CAS-A. And we have actually several weeks observation of that. We'll be getting data down all the time. And so we expect to have results very quickly from that source. So I should just say there's a month of commissioning. So that will be early January where we would start getting those data back.
Great. Continuing with our science questions, how is what IXPE looks at, how is its science different from the James Webb Space Telescope, which is also launching later in December in a very different kind of mission?
I'm not sure. Well,
That's a very hard question. So first of all, it's a different wavelength. And it's a very different type of program. I think we're gonna observe fewer sources. And one of the keys here is what Brian said at the beginning. To measure polarization, we need very, very long integration times. And so the way IXPE will work in the 2 years of the mission is that we will point and stare at a few sources. Well, I should say probably a few dozens of sources in 2 years. We're not gonna do any large-scale catalog type science, and of course, in a different wavelength.
So, if I can just add, so I think that we are, as Luca said, it's a very different wavelength, and just speaking in sort of generalized terms, in infrared, you're more looking at the early phases of stars, whereas we are looking at the dramatic sort of end life of stars.
That's a nice comparison. I like the different time frames that each one is looking at. I will also add, from my perspective, NASA does missions of all shapes and sizes, and they're all important for the portfolio. And one of the things IXPE is doing is this really targeted research focus, and that is also one of the things that separates these. All right, let's go back to those black holes. We have a question about what, in general, are we going to be able to better understand about the black holes. We talked a little bit about the spin, but are there other things we can learn? And I know we talked earlier about the black hole at the center of our galaxy, so maybe we can talk about that.
Okay. So we have a supermassive black hole at the center of our galaxy called Sagittarius A, or A star. And that black hole is very inactive, which is a bit of a puzzle because we'd expect it to be much, much brighter than it currently is, given the fact that it's a million solar masses. And so we suspect, though, that it was much brighter in the very recent past. And so IXPE is going to make a measurement that can prove that. There are molecular clouds that are a few hundred years of light travel time away from the galactic center. And we see those clouds glowing in X-rays, although there's no source of X-rays within them. So we suspect those X-rays are reflected off the Sagittarius A, the black hole, the supermassive black hole at the center of our galaxy, a few hundred years ago, because that's the light travel time to these clouds. So we make this measurement with IXPE. Now, if it turns out, because of the geometry, the X-rays would actually reflect through 90 degrees to get to us approximately, and that produces highly polarized radiation. So by measuring whether these, the emission from these molecular clouds is polarized or not, we can tell where the emission, the driving source came from. In fact, the angle of the polarization will help us point back to the direction of the source. And so we're hoping with that to show that in the very recent past, which I find quite remarkable, I mean, it's not a geological timescale, it's just a few hundred years, that this enormous black hole was maybe 1 million times brighter.
And if I can add something, so one of the characteristics of these extreme sources is that they're under conditions that is essentially impossible to reproduce in our labs. You know, some of them, as Brian said, have a magnetic field that's millions of times higher than you could possibly achieve in a lab. For black holes, the main point is that there's around the space-time around the black hole. It's curved, and you know, the source is in what's called a strong field regime. And this is the interesting part, because general relativity, which it's our theory that describes this kind of system, makes very specific prediction as to how the polarization behaves in these systems. For instance, you know, one of the most striking is that you would expect the polarization angle to flip at some point in energy. And so if we were able to measure that, that would be a confirmation, indirect confirmation of general relativity that we would have no other means to get. So I think that's pretty exciting.
All right. We've also gotten a question from social media about X-rays in general. Luca's been talking about how, you know, an X-ray source comes from all these interesting things and then travels all the way to our detector. But what are those X-rays? Are they the same thing as what we see in a medical scan? Are they the same kind of X-ray?
Yes, I mean, X-rays are light. You know, there's an entire continuum in the spectrum of electromagnetic wave that goes from radio waves to gamma rays. And so the X-rays are this region that's sitting in between, you know, ultraviolet and gamma rays. We're interested in a very specific band of X-rays, which is, in technical terms, it's a 2 to 8 keV, roughly. So that would be slightly lower than the typical energies that you would get in medical facilities, but it's effectively exactly the same thing, yes.
Great, thank you. We have one more social media question, but again, if anybody on the phone or in the room wants a question, raise your hand, but otherwise, this may be our last one. So this question is about what happens when polarized light travels through space, specifically magnetic fields. The question is about whether or not we will be able to use polarized X-rays to understand better about the magnetic fields in space.
So this is a very, very good one. Yeah. And the answer, again, it's, I think, possibly yes. So propagation through cosmological distances can affect polarization. We know very little about the intergalactic magnetic fields. We don't really know very precisely the magnitude and the scale of the magnetic fields, but yes, the polarization might be affected from propagation. There might be exotic processes at play. There might be, particles that we haven't discovered yet that might affect the polarization. And so, for sure, there's people among the theoreticians that are thinking about this and trying to understand whether, from the measurement of polarization from very distant sources, we can learn something new about fundamental physics. So that's another very, very exciting science topic.
There's also, sorry.
Please go ahead.
There's also a phenomenon called part of quantum electrodynamics, and this is a very bizarre phenomenon, but it's called vacuum birefringence. And this takes place in extremely strong magnetic fields. And so we have these sources called magnetars that have, 1,000 million times the magnetic field of the Earth. And so we expect to be able to measure this phenomenon, this vacuum birefringence, in these sources, these magnetars.
Well, thank you everybody so much, and thank you so much for joining us. Those are the ends of our questions for today. If you want more information about IXPE, please go to nasa.gov/IXPE, IXPE. And a reminder that we are launching at 1 a.m. East Coast time on Thursday, December 9th. Our broadcast starts at 12:30, and you can watch that at nasa.gov/live. Go IXPE, can't wait to see what we find. Thank you so much, everybody.